welcome. Thanks for coming to the first talk today. Thank you for coming to Scala Swarm. And let's get it off. So, for this be madness, the first method int. There is a bug in this slide. If anyone spots the bug right away, I don't know, you get like a prize. And it's not a grammatical bug. It's a bug about a mismatch, a semantic mismatch between the Hamlet quote and what the hell is the samurai doing here? Hamlet wasn't really a samurai story, or was it? And sometimes you get people like that, like, oh my god, it's completely wrong, doesn't make any sense. And what I will try to do in this talk is to try to persuade you to not be that person in general. Not about that slide, you can say it about that slide. But sometimes, especially it's easy online, I don't know, you write some API, you use some framework, you use some tool, you maybe don't like something in the language or this library, and you go to Twitter and say it's, oh my god, this is complete crap, doesn't make any sense, did that person who wrote that thing have no brain, etc. And I think we sometimes very often forget that tools and libraries are never, at least the successful ones, are never really created in a vacuum. They always have something that maybe forces the author to go one way or the other with some design. And similar to that slide, like you look at it, yeah, it doesn't make any sense, but maybe it does make sense if you had more context about it. So this is what I try to get to in this talk. And it will be about programming, don't worry about it. But to understand that slide, you basically would have to know about Akira Kurosawa, who did the movie from which that screenshot was, which is The Throne of Blood, which is a Macbeth adaptation. So there's a mismatch. We're getting closer. So the quote is from Hamlet, but the screenshot is from Macbeth. Not quite the same thing. But when you think about it, okay, so it's all linked to Shakespeare and it has some kind of meaning, has some kind of sense. Technically, if I were to make a correct slide with a more correct adaptation in a screenshot, it would be this, which is the Hamlet adaptation from Kurosawa. Again, pretty old movie, so you may not know that. But again, it would be a bit confusing if you didn't have the context, right? Businessman, Hamlet quote, again, doesn't make sense until you have context. And with that, let's dive into Scala Swarm, the first day of it. And let's get in the mood of actually understanding and learning about stuff in depth instead of just looking at it superficially. Because if you look at things superficially, you may get the either wrong idea or just a very superficial and not very educational understanding of something. So let's not do the superficial quick look at things, let's try to dive into stuff a bit deeper. So who am I? I'm Konrad, as introduced already. I work on the Akka team at Lightband. I wrote a mini book, I participated in the Reactive Streams initiative, and do a bunch of community work in Poland, including the Geekon conference and some other stuff. So enough about me. That's the project I work on. Has anyone not heard about Akka in this audience? Who has heard about Akka? Okay, so you're not asleep, thank you. Thank you for waking up so early, especially with all this good wine around. Who's using Akka? A lot of people are. And let's go to our first failure. Yeah, null. It's obviously not a bug in the slide, but it is, how many people would call it, a huge, huge mistake, including, was it Charles? Well, Sir Hoare, who called it a billion-dollar mistake. Obviously, being a Scala developer, you all here know that nulls are not a nice thing to have, and we'd like to not have them at all, because they can make this code fail, right? Here's a small quiz. What can this code do? Well, we would like it to do the summing, right? It says calculate sum, so maybe that's a calculator, maybe, hopefully. So what could it do? It could return 4 if we're lucky. It could return something else if it was wrong, but it could also have a null pointer exception, just if something is null, if something inside there is null. You're never ever safe in the presence of null. You'd have to check everything all the time. We don't do that, right? We kind of assume, yeah, that's never gonna be null. That's how we live with this. The third answer is something that Victor always brings up from my team or company, which is, yeah, technically it could be even worse. It could just exit for JVM. Yeah, it could. It's not a very helpful answer, but it would be a valid one to answer as well. So, obviously in Scala, we have a solution to that. We have it in the form of options. And timeline-wise, historically, Scala had it pretty early. I mean, it's not like we invented it in Scala. It's a pretty well-known concept, also known under the name of maybe. So something maybe has a value, maybe it doesn't. But in Scala it was pretty early on, and probably even in earlier versions, but that's the oldest one I could find by quickly Googling. And then even Java kind of figured out, yeah, this null thing is not that good. Let's maybe introduce it. At least the Guava guys did in 2011, introduction of optional, which basically after a few years became the Java's optional. It's pretty much very same API with very small differences. So we have it in Java now as well. Now let's talk about, well, maybe mistakes here. How you should be using this API is usually, well, option you match on it, right? Do I have an example? Yeah. So in Scala, when you use an option, you can either for each on it, and if it had a value, you go inside it. And that's a nice way, because you only have one place and kind of one path this thing will execute. You can get a bit better, well, a bit different or worse, some would argue, with just matching on it. And then you have, well, you have two code paths, but you can handle the empty case, right? And compare that to what you can, or what people do in Java, which is you do the optional is present, and then you do the optional get. So the problem we have here is, what if someone, I don't know, refactors things and removes this line? It's the execution of this to uppercasing is not directly linked with the execution of the check. It's in two places, right? Whereas in the for each case, the check is kind of implicit. It's there, right? This line will only ever execute if the value was there. It's always safe. And if we have it in two places, so like the match is a bit better because at least it's very explicit what you have here. You can't get the value in the none case, right? But the if case, it's very imperative. So again, are designers of Java libraries just not very smart? I don't want to say that. They are really smart people. Just the background of the language and how people abuse the language a bit, because you could do the same in Java. But people don't, because they come from an imperative kind of background, and the if feels natural. So, and why is the get bad? Obviously the get is bad because it can throw a no such element exception, which is kind of like a null exception. We just changed the exception type, right? Not very helpful. So can we do better than that? Okay, we know we made some mistakes. We kind of came from imperative programming in that API. And what could we do if we had a blank slate and we were to design a new API? Because there, obviously, the option type had to somehow fit into existing usage patterns, existing styles. But what if we have a new API to design? How would we do that? And we'll look at a specific API, which is the Scala Futures, where we separated, the Scala Futures kind of team, committee, separated the bad things from the good things, right? So remember the get and the map, which is the good API in option. So what's the bad thing you can do in a future? So obviously when you do asynchronous programming, blocking is really bad. And if someone doesn't know why, here's a quick summary. Because blocking basically wastes resources. So if you have a future and you block your thread until the future has completed, then basically you have taken that resource, that CPU, from anyone else who could have been doing stuff. And it's a bit wasted, right? Here another example, if you wait for an I/O write to complete blockingly, like an await result, or a get on a Java future, that's again wasteful. So we want to discourage people from using the blocking APIs. Here's another example. If you know Akka HTTP, something I worked on and still do for a long time, there sometimes people want to benchmark, quote unquote. It's not really a benchmark. They want to try, oh yeah, so what will happen if something does like slow stuff in my future? And they write this code. They say complete, so this means if you get a post request, complete it with the result of this future. And they do this sleep inside. Now the problem is, when you do that and you keep hitting the server with a lot of requests, basically the sleeping dominates the entire program. So instead of actually running, so the running is like this part of the slide, it's just sleeping. And people call that a benchmark. It's not a benchmark if it only sleeps for whatever time you gave it to sleep. So again, we want to discourage blocking. So the Java API, again, the first one is the blocking get. And again, let's think about, yeah, didn't they know better to not expose this get method? It's terrible. Why would anyone do that? Well, again, they had more context than we do right now here. And the reason this get method exists here is because it always existed on the future here. And even when they introduced a new API, they kind of wanted to live in the same ecosystem as the older APIs were expecting. So whenever you use a completable future nowadays, you can pass it into what was expecting just a future. And sadly, that means implementing this blocking get method. So this could wait forever. But it's not like people are stupid. People learn with time. And we have a good overload, right? It has a timeout. So we will at least block at most this and this amount of time. So in the Java APIs, you see it's still in the same place, right? The really, really bad one and the slightly less bad one, it's still on the same interface. Again, because a bit historically, that makes sense. It feels right for users of the previous versions of the library. And what did we do in Scala? So in Scala, when you see the future trait, I hope you can see it's a bit fuzzy, but I hope you can see. There is no get. You can't get on the future, right? I'm sure you've experienced that, maybe first time learning Scala, first time you're working with futures, and you have this question, okay, I want to get the value, but you can't get the value. Why can't you get the value? Because we want to discourage using that blocking API. It doesn't exist, so if it doesn't exist, you can't do the wrong thing. What does exist is the value method. It looks kind of like the get, but it doesn't block. That's why it's option of try. So it may have completed, which is when it's a sum, and then it may have completed with a failure or a success, which is the try. So we nicely compose the types here, and this is a non-blocking API. So we exposed a nice version that maybe you could poll if you really want to. But what is this awaitable here? So awaitable is our trick to get this separation of API working, where we say, hey, well, actually, there is a way you can await on this future, like in the blocking bad way, because sometimes it's useful, right? Sometimes in testing, or if you know it's completed, you want to actually await on it. So in the Java one, you have the get. In Scala, you don't have the get, but what you do have is the await object. So that's the difference. We separated the bad stuff into a very explicit way. And the linkage here is that internally, every awaitable has some API that's kind of hidden from end users. But you can use it because you have a contract between the awaitable and the await. When you implemented the await, you kind of use the backdoor and do the blocking there. But what we did is expose it very explicitly. You see the blocking in the code, it says await, it says always a timeout. So there isn't a infinitely waiting one. You could wait infinitely, but then you would say at most forever, right? duration infinite. So it's very explicit. How could we pull that off? We could pull that off because it was a new API back then, right? So again, different trade-offs and different priorities. Okay, so probably people already know where I'm going with that one. Any to unit. The probably the most laughed about and like thing that people point out about Akka is how can you have this type at the core of your thing? It's not like we didn't think about types. We are actually Scala developers. We like types. It's just that there's a certain impedance mismatch between strictly typing and distributed systems. And when people look at actors, because the any2unit is basically an actors thing, they sometimes forget that actors are not only a concurrency thing, but they are first and foremost a distributed computing thing. So many nodes, things can fail, messages cannot arrive, etc., etc. So it's very different from just local programming. And I'm not making excuses, but I want to kind of explain why it's not as trivial just add a type there. And it's also not that we don't like types, because the last 3 years or so, we've been very focused on Akka Streams, which is a fully typed API, right? So we've been working on that. But Akka Streams is actually a local abstraction, so that's why it was simpler to introduce typing there. Well, it felt right. It was the right thing to do in the first place. So here's an actor, if someone has not seen an actor. Has someone not seen Akka actors before? No need to be embarrassed if you haven't. Okay, one or two hands. So that's an actor. What it does is you have this receive method, and it gets messages, it pattern matches on them, and then it can strictly do one of these things. It can react on the message. So actors are always driven by messages they receive. They can't do anything else. They can send other messages, so like, yeah, sender okay. They can spawn child actors, and they can change their behavior. I should have actually changed that slightly. But that's kind of reacting on a message. That's changing your behavior. So this context become working. And this is where the problem with typing the receive method comes in, because here we only handle work now methods, messages. But in the working state, we handle a completely different set of messages. But we have no way of changing whoever sent us a message. We can't change the type they have in their hands already. They could still be sending work now messages, which is kind of the origin of any2unit story and the strong Erlang inspiration, obviously, right? So there was attempts to fix that. Like I said, it's not a new thing for us, and we did try to fix it many times and failed many times. And the first thing we had was the typed actor API, which never was meant to solve what I just showed, actually. If you've seen the typed actor, the naming is a bit confusing. Typed actor is the old API. Akka Typed is the new API I'll talk about. So it's deprecated, never ever touch it, doesn't make any sense. But why doesn't it make any sense? Specifically, here's examples how you would use it. Back then, that was one of the first Akka APIs Jonas implemented with Victor. And the purpose of this API was to not scare Java people away, to make it feel more Java-ish, what people would be used to from Spring or whatnot, just calling methods. But it also allowed the really bad API to happen. Because here the square, you send an int, you get an int back eventually. That's okay. We're not a big fan of RPC calls, but yeah, that's reasonable. But the really bad one is square now, and then you blockingly wait that you get the int back. So that's the worst thing you can do in distributed computing, act as if the distributed thing is actually not distributed. Because this could never return, messages could get lost, etc. So this is wrong, don't do it. It's also slow, it feels RPC-ish, doesn't make any sense. So then we attempted typed channels. So typed channels, a bit inspired by ghost channels, although a bit different, in semantics at least. So that was the second attempt to actually solve the untyped actors problem. Yeah, the code is a bit fuzzy. So I can zoom in a bit. Basically, the problem we faced with the typed channels was, well, the type signatures would get pretty big. It wasn't that easy to use. We made the mistake of adding too many operators, which you may know is not a good thing. And nowadays in Akka we only have 3 operators: the exclamation mark, which is sending a message; the question mark, which is like a request to reply; and the wiggly arrow, which we'll get to in a second. But this was way too much, well, over-engineering in a sense, and it was also requiring macros to actually work. And one of the rules we have in Akka is that all of the APIs have to have a native feeling Java API as well. And we're in a Scala conference, so probably most of you don't care as much about the Java API and that it's on par, etc. But very often when you're this person interested in Scala and trying to introduce it to a team, and people would be a bit afraid of it. But when you have the ability to say, yeah, we can start with Java, or we can back out to Java, it actually helps get into these companies and get into those teams. And eventually they'll realize they want to write Scala anyway. So very often that's how people come over. So typed channels, sadly failure. We tried, but wasn't quite the right thing to do. They're dead again. So then many years, well, like 3 years or so, including some new white papers, because this was an area of active research, like actual academic research, has not really solved typing in distributed systems properly. But the Reactors paper by Alexander Prokopec and Martin Oderski gave us a new idea. And we arrived at Akka Typed, which is the current thing that you can actually try out now. It's released in Akka 2.5.2. We're still experimenting with the API, but it will not change that much. So we're pretty sure that's pretty much what it will be. And we exposed 2 styles. Again, if you wouldn't have context and someone tells you about, yeah, they have like 2 new Actor API. And one is Actor.mutable, and one is Actor.immutable. And maybe you would become that person from that first slide we showed, like, oh my god, this doesn't make any sense. But there is a really good reason behind both the naming and the reason we have 2 APIs and not 1. So let's dive into it. So firstly, what does Akka Typed actually change? The actor-refs are now actually typed, right? So it's actor-ref, which is where you send the messages to. It has a type T, which is the messages it can handle. The core concept, instead of extending actor, you use behaviors. And that's an interesting change because composing behaviors, you can, a bit more in the functional programming style, you can compose them rather than in the proxy composition style we usually did with actors. And sender is gone. Is anyone missing sender? Do you feel, why is sender gone? I like that. 1 hand. 2 hands. Tomer likes it. Okay, that's surprising. So sender being gone is actually a good thing, in my opinion. Because for those of you who don't know, you can always in an actor say, okay, who sent me this message? And you get an actor-ref back. How would we do that in a typed fashion? You wouldn't be able to get the right type there, right? Because it's just a method, it doesn't have context from that message, what the type of the sender was, what it can handle as a reply. So by shifting the sender into the message type, you can always decide when you send a message what you expect to be sent back to you. So when you send a give me money request, you can send yourself with a type that says, like money request response, which would be like, yeah, okay, here's the cash, or no, sorry, I can't give you cash now. And it's fully typed. There's also funny implications on the infrastructure. We can go way faster without having the sender, but that's like implementation detail. So back to the 2 APIs. We have Actor.mutable, and on the left-hand side you have usual actor, which you know and have seen on previous slides. So the reason we have the mutable one is when you look at the old one, you extend an actor, you receive messages, you can modify some stuff. It feels very simple, right? This is the actor, this class is the actor class. And in order to facilitate an easy migration to, well, at least now I have types on my receives, we wanted to have the same style, which is the actor.mutable behavior. And it's pretty much the same. You'll see that the on message now, instead of receive, has the type that you have here, and that's the type of message you can actually handle. And a behavior basically means that the become that used to be implicit, you could say context become, is now always explicit. So we're closer to the actor model. We're always telling you, okay, so what will you do next? And then you say, yeah, the same thing I was doing right now by returning this. But here's what the functional programming aficionados would prefer, probably, which is the immutable style. So the big difference is, in the immutable style, it's all about functions. And we basically create an actor. We have this factory, actor, immutable, it handles commands. And then you get a function with context if you want to do like spawn child actors, etc. And you get the message. What's difficult to do in that API? Keeping state around is, well, you could, especially in Scala, you just make a closure, you close over state. But in Java, it would be impossible to just close over stuff because things closed over by in a lambda have to be effectively final. So it's not as easy if you have an existing code base to migrate to, well, the recommended style, which is this one. But it is really easy to migrate to the mutable style. And because we have this kind of obligation to help people that have wrote software with Akka for many years to make the migration path easy, we did the mutable style. So now you perhaps understand more about why two styles. So immutable one in Scala, and yeah, Java will eventually get pattern matching. They actually proposed that recently to maybe work on it. So that's, again, one of those things that Scala kind of didn't really pioneer, but brought to mainstream. And even Java now looking at it. But until Java actually adopts that, we provide some kind of factories and help us to write similar looking API. Quick question. Should I zoom in on code because it's not readable if I don't, or it's actually readable? Is it readable? It's not. Is it not readable like that? Yeah. Oh my god! Oh my god! No! This is how I feel when I. Oh my god! So if you want to try Akka Typed, it's out there. You can try it. Documentation isn't like up to our standards yet, but we did a bunch of blocks because right now it's in a phase where we want aggressive feedback. So look at the blogs, give us feedback, and give feedback in a way that, oh my god, this is completely wrong. Not that style, please. Just what is wrong, what is not working out for you, and then we can fix it. So that's maybe not a new thing for Scala developers like yourselves, but what if we never mutated things? Oh, and here's a good joke about it. Like code written in Haskell is guaranteed to have no side effects. Is it because it will never run? But the same about mutating stuff. So this is perhaps back to basics, but also very interesting one. So in Scala, we have kind of two axes to mutability. One is, so the x-axis here, the data type can be mutable or immutable, right? You can have a mutable list or an immutable list. And then you have the reference to it, be a val, a value, or a variable, right? Easy. And one would argue that having val as a default is a huge game changer, at least for me, because when you write in other languages which don't have an immutable reference as a thing, you start to panic that, oh my god, some people will be mutating my stuff, but I want to have like immutable references. So obviously, val plus mutable, that's happy path, that's a fact. No one can ever change that. A variable plus immutable data structure is actually pretty good. That's pretty good because if someone gets a reference to it, and you give someone that list, you give someone that data structure, they can't break it to you, right? They can't like insert random stuff into it. They can just look at it. Ah, okay, so that's the things you have in your shopping cart. But they cannot insert embarrassing items into it. A mutable value, yeah, you lose that ability to share the data structure with someone in a safe way. Right? So when you share the mutable one, and you may find yourself with embarrassing items in your shopping cart. You don't want to do that. And the last option here is a mutable var, which doesn't make any sense at all. Because someone could be mutating the reference to it, and someone could be mutating the insize of it, which is like two access patterns that are completely different, and you have no idea what's going to happen. That's the default in many languages, when you think about it. You have mutable data structures in mutable references. Thankfully, more and more languages getting like a const or a val or etc. Again, a bit following what we did there. Yeah, that's how it looks in code. I'm sure you know that. Easy to spot just by having a mutable prefix. If you use an IDE, you can configure stuff to just highlight the mutable ones with red squiggly lines. I recommend that actually. So we talked about never ever change, but what about never ever delete and appending only as a way of life? And again, let's think about it. Maybe you know where I'm heading with that, maybe you don't. But if you think about, okay, let's only ever append facts. You have your stone tablet, and whenever you get a transaction, you will write things to the stone tablet. More facts, write them, and then you need a bigger tablet, right? We can fix that. We can get a bigger tablet. And thankfully, unlike stone tablets, disk is really, really cheap nowadays, right? I mean, getting disk is the cheapest thing you can possibly get on a cloud thingy. CPU, not so much, right? But disk is cheap. And what is a delete? What is an update? Because this is a stone tablet, at least we imagine it is a stone tablet. We can't write a delete. I mean, you can say, hey, that record previously, let's treat it as if it never was there. So this is basically event sourcing, right? It's nothing surprising, perhaps, because this is how accounting and anything that has a source of truth or like a audit log, that's how things work. You never delete stuff from an audit log. You just say, yeah, that actually, let's not consider that thing to have happened because we undid it or something. So why would we do this very complicated thing where we ever need to have ever-increasing stone tablets? For one thing, because then we are independent of how we will query this thing in the future. So we get an audit log for free, which is usually, sometimes, not usually, sometimes very important. And we can, for example, if you were appending to your travel, you have like a travel log, and you keep appending which cities you went to. And maybe then you want to query stuff about which are all the friends of me which I could have visited on that trip. Then you can prepare from that trip, enrich the data a bit, put it in some optimized query state for that query. So the query dictates how you will actually structure the data. Or if you want to have, I don't know, like a graph query. Was this the fastest way I could have traveled these some cities, etc.? Then you maybe want to use some graph database. And by having all of the facts stored, all of them, we can always do this projection to the other side, to whatever we want to query. We could not do that if we were updating in place and the only data I would have is, okay, in which city am I? Right? You lose the history of stuff. So by doing something slightly differently, we get some, well, not unsuspected, but kind of related benefits. So as I keep saying in this entire talk, API is always with context. It's not in a vacuum. I talked about the squiggly arrow. Yeah, so this is an API we have in Akka. Like I said, we don't usually do operators. We only have 3, question mark, exclamation mark, and wiggly arrow. Wiggly arrow is pretty much a power feature you probably should not use at all, unless you have a really good reason. And what it is in Akka streams, and maybe let's ask the question. By looking at this API, okay, you know, well, the tweet says, but feeling when your Akka streams graph flow, some graph, okay, gets crazy. I certainly agree, that's crazy, that's total abuse of that API. But by looking at it, do you know, like, what was the intention of that API? What was it designed for? I have stickers as prizes and stuff. Anyone? Any ideas? Tomer?
Wiring bits of behavior together into a full-blown like pipeline for data. Something specific. I don't know what this does. It's all characters, but
yeah.
It's pretty clear how things wire up together into the whole graph and
yeah.
response ends up.
Yeah. So repeat for the recording. The suggestion was that, yeah, this probably was designed to do some kind of connecting stuff together, but at least it does show what stuff is connected to where, a bit like a wiring of stuff. And yeah, indeed, that was kind of the purpose. Here it's certainly a bit overdoing it. So like every API, stuff can be abused. So here's a real-life scenario for which we designed that API. In my office, like home office, I have this wall. That's not a capybara, sadly, that's just a hamster, but it's surfing. But we want to look at that part. This is actually the Akka HTTP server pipeline. So on the right-hand side, you see the request parsing. The BS is not bullshit, that's byte string. So byte string in, you do request parsing, there's the HTTP controller, so it does things like, oh, okay, what should I do with this request? Then request preparation, so some enrichment. The app flow is basically the user's application transformation of request to response, and then it goes back to the user, to the network. We render the response, we render the byte string onto TCP. So this looks kind of like a graph. This is exactly what we have in the code. So this is just a screenshot from the Akka HTTP blueprint, how we call them. And so the one on my wall was a bit simplified. I didn't have one-to-one BD, but basically it's exactly that. Arrow, stage, arrow, stage, arrow, stage. So that API was specifically designed to look like the drawing you can possibly do on a whiteboard. Did we pull it off? Kind of. Do we actually use it as much as we thought we would? We actually don't. Because things sometimes get a bit too big with a wiggly arrow. But at least, here's how it can look like. So HTTP in to the request preparation to the HTTP in, which is the user land. Here from the user land, response is coming out. It goes to the controller goes to the rendering pipeline. It goes to network. So when you look at that at least kind of makes sense. The one with 5 million ones with single letters, that probably doesn't make much sense to anyone reading that. So again, it's about context, and things can always be abused. And I said that's not really an API you should be using most of the time, because the API we actually worked on very intensely is these flow source sync APIs. Why did we pick 3 different words again? If you're familiar with, I don't know, like RxJava or other FRP-like, it's not quite FRP, but similar libraries, they usually talk about maybe observable or iterate or something like that. We have these different names because we deeply care about naming, and the flow is very different from just the source of data, and it's expressed in type and how you can connect to it. You can't just start writing data into a source. It's a source. So few last topics. Am I out of time? Not yet. So again, the messaging as a first-class citizen is pretty much the hacker way, which is how we think about everything. So we think about messages, not method calls. And again, this we've seen. This is a quote from Alan Kay, pretty much the person coining object-oriented programming. If you haven't seen that quote, let me just highlight the interesting part. So I'm sorry that long ago I coined the term objects for this topic, and now the interesting bit, because it gets many people to focus on the lesser idea, the objects. The big idea is messaging. So obviously this is way back in Eiffel and Smalltalk, sorry, Smalltalk, not Eiffel, where objects would communicate with messages. And when you think about it, that's how actors communicate and not how methods communicate. And the difference here is when you have a method locally, okay, this we talked about, the calculate sum, what it can do. But what if it's parallel and what if it's maybe distributed? And this should be a build out automatically, but isn't. But once this gets distributed, you get a whole can of worms, which is, okay, what is actually put on the wire when you call that method? You don't really know, right? Because somehow these two numbers and this method name have to land on the wire. How can we retry on a different host? How can we directly respond? Can we do like a proxy response where I ask someone, and that guy asks someone else, but that someone else replies directly to me? Can we do that with this RPC style? Yeah, maybe we could do that. We could do like a special API, etc., etc. There's a lot of questions here. But what if we just make it a message? So locally, you send a message and the message maybe arrives or the entire VM crashes. Could happen. That's the only single two things that could happen. So what can happen if we do it in a distributed setting, remotely? So what is put on the wire? Well, exactly that message. That is exactly what will be put on the wire. We exactly know how we would serialize that message because you configured that. Can things blow up if network blows up? No, just the message cannot arrive. I don't know, can someone block us from sending that? No, they can just not receive the message. So instead of having these many cases of how the API can fail, we only have a single way how this entire API can fail, which is someone will not get that message. So actually we have very simplified like the spectrum of errors we have to think about. It's only one kind of failure, it's not getting the message. And we can do very easily patterns like the direct response. So if I ask someone, that person asks someone, they can reply to me directly, which isn't that obvious in RPC land. You can pull it off, but people usually don't. And you would have in RPC land, okay, that downstream replies to this one, and the problem is, well, then you have like added latency of all the communication, and everybody serializes and deserializes the same message all the time. So again, messaging, solving some things that are perhaps not as visible up front. Why the hell would anyone do messaging? That's the answer. It actually opens up a lot of possibilities there. And then you get the angry guy again. Like, oh my god, I can totally do that REST and HTTP. You can. Did you ever see an API which actually did that? People don't. Because you would have to accept the first request with maybe a accepted, maybe with a no content. I forgot what 202 is. Well, if anyone remembers, shout out. And it's quite some overhead, because then both sides need to become a server, because you need to call them back. No one does that. And in messaging, you just are ready to receive a message. And it's cheap. And again, in just methods and objects, what happens is we talk about encapsulation. Oh yeah, my god, I'm so object-oriented. I encapsulated my state and I'm testing my complex logic. Oh, but testing is hard and I'll just expose the state. So a wired getter appears. And then people say, but it's only for testing. it's never only for testing. The entire code base gets polluted with exposing the state depending on it. And in actors, you can't possibly ever expose the state without really working for it, right? It's very easy to expose behaviors. It's very difficult because this is not even the type of the actor. That's only the ref. You have no idea what the actor class is. And this is good. This helps encapsulate the state. It helps you write code that does not depend on the internals of that actor. So again, sometimes people, when they start with actors, they're like, oh, this is crap. I want to get the internal state. No, you do not want to get the internal state. Trust me. It's better for the long term of that application. And I think last topic I'm having here. So naming things is probably one of the two hardest problems in computer science. The other one being cache invalidation, and the other one being a one-off errors, as you know. And this entire idea came to me when I talked with Roland, and he had his idea of writing a blog about I want my words back, where he would get really angry about people misusing or changing the meaning of some words. For example, hipster. Like hipster used to be a thing that keeps your trousers on your hips, and not a coffee-loving, bird-wearing person. So there's two words I want to have back. One is scheduler, and the other one is stream. Now think about what you think when you saw these words, because it's probably completely different from what I think about when I see these words. And if it's the same, then yay. So a scheduler, what does it do? Well, we talk about, yeah, you know, it fires an event at some point, but this could be anything. You know, it's very ambiguous what that actually is. And then people come to Akka and they see, okay, I have this problem, that's the end of the word. I need to start screaming once the end of the word is happening. So, there's a scheduler, awesome. So schedule once until end of word, so 127 days. I will send then to myself a message that is, now it's the end of the word, and then I can start screaming. Excellent. That's my reaction to that API, that usage of that API. Like, don't. And I highlighted in red why that's not what you actually want to do. The Akka scheduler is designed for a specific use case. And this is not that specific use case. This is scheduling something far into the future, which probably should persist. And if you redeploy apps, you don't want the end of the word time to move, right? Because you restart the app, and it again schedules it that many days in the future. But that's kind of wrong. You want to schedule it on a specific date because the Mayan calendar said so. So it's the same name, but it's a completely different use case. So to understand what it's actually optimized for, we have to go into the dungeon, the Akka Actor dungeon. So technically that class is not in the dungeon, but we refer to all of the internals as the dungeon to imply that you should not go there because you may lose sanity. So the Akka scheduler has specifically this single guarantee. Fire an event no sooner than in this amount of time. No sooner than. No strong guarantee about exactly at that point in time. The only thing we need is no sooner than. Why do we need that? Why? Because we have a lot of events. We have like millions, tens of millions of events per second, perhaps, because you're an HTTP server, or you're just firing off futures, and every future you have in your system has a timeout. And you know, if you're doing like hundreds of thousands per requests per second, everyone starts some task that's doing something in the back, that ends up being millions of futures. And then all of them have the same timeout, right? So within a second, if I don't get a reply from my database, fail the request. So the Akka scheduler is optimized for a lot of events, which we put into these buckets. And this is kind of the time. And as time passes by, then we look at, okay, so which events have we not triggered yet? Which buckets have we not triggered yet? Which is why we get this impreciseness, because we move this time forward by a few milliseconds, and that means the precisest we can get is, a thing can get as late as 10 milliseconds after the thing has actually passed that point in time, right? It can never trigger sooner, but that's fine. We only want to fail the future after 10 seconds or something. So that's what we're optimized for. Huge amounts of events, a constant time insertion to this data structure, and really high performance turning the wheel of time in a sense. It's not precise, never was meant to be, never will be, and it's not persistent, because then it wouldn't be constant time insertion, high performance inserts. You don't want your future timeouts to be persisted to disk. You don't care. But here's a fun fact to brighten up a bit. So that's a funny story about like cooperation of two open source projects. Initially, the scheduler we have, that's a we call it Lars, the light array revolver scheduler, was very inspired by the Netty one. Then we fixed a few things, optimized it a bit. Then the Netty project pulled in these changes and back and forth. 5 minutes. Okay, perfect. So it's nice when open source projects or just people cooperate like that instead of claiming, oh, our scheduler is better or something. I really enjoy when people cooperate like that. But here's the fun fact I promised. So because the light array revolver scheduler is called Lars for short, which we thought sounds like a sailor. So when it can't start a new thread, it says, Lars cannot start a new thread, ship's going down. You will probably never see that error. It will only happen if you run out of physical memory on your box. But could happen. Okay, so let's talk about this Mayan calendar and things blowing up. What would you need there? Okay, so in 127 days, end of the world, we need to start screaming. So we need to be persistent, because if the app fails, if entire cluster fails, we need to still remember if we actually scheduled that message, what the message should be, etc., etc. So we need persistence. We probably need replication, because we really need to start screaming, and if the database, one node, fails, we still want to have that something. And we only want to start screaming once, right? Only I want to start screaming, maybe the rest of the planet doesn't care, so we only want to trigger that once. So what do we need here? We want something like cron, retries on failed tasks, etc., etc. And, oh, do I miss a slide? I do miss a slide. Well, so it's basically I'm referring to Chronos or just some other library that has that as the use case. So let's finish up. So Quartz is another one that's optimized for that story. Stream. I did run out of a bit of time, actually. So Stream is another one where you have 20,000 projects calling themselves a streaming thing, but everybody does it differently. You have Kafka streams, which do completely different things from Spark streaming, which isn't streaming, actually. It's more like windowed batching. And then you have Java streams, which aren't really streams, but they're like bulk collection operations, but we still use the word stream. And then you have reactive streams, which is an API we worked on, but again, very different use case. And TCP itself being also streaming. So, to sum up, everything is a remix in the sense of even the words get reused, meanings get diluted, and without looking like deeper at a thing, you can't possibly understand what it actually is, because words get reused, meanings get changed, intentions are maybe not visible from the outside. So I would recommend you, so during these days here, to when someone presents an API and you think, oh, this is weird, to come up to them, maybe ask a question like, oh, why does it do that? Like, does it have to? Because perhaps there's a reason. I wrote a mini book, and we have a few minutes for questions, maybe. Thank you very much.
So As always, we started a bit late because of all the sleepyheads. That's why we lost a couple of minutes. Sorry, Konrad.
Yeah.
I guess we can allow one question, the rest during the coffee break,
Yeah.
which is until 10:15. So I will allow for one question. So are there any takers? Any takers? I have a question here.
So following up on the sender going away thing, first of all, just to qualify, I don't have a problem with the current sender API going away because it kind of sucks. But what I'm curious about is how do you actually implement certain things that it allows? So one like canonical use case that maybe is discouraged is proxy objects that just take in messages, pass them on to something, and then switch the sender so that the response comes back to the upstream.
The forward pattern.
Yeah.
Yeah.
So how do you implement that if you don't have, like, you can't force the upstream to actually include that in the message, and you don't even know what the message type is if you're a general purpose proxy? How do you implement that?
Yeah. So basically, it would have to be modeled in the type. If you are this proxy actor, previously you would rely on the magical sender value, which is gone, correct? But one could argue that what we did like magically in the back, which is basically when you send a message, what we do is we allocate an envelope, we put the message inside, and we also put the who sent the message in that envelope. So basically, instead of us magically putting the sender inside there, you would do that yourself. You would say like, maybe we'll even include an envelope type to be explicit, because I think that's a common pattern. Like an envelope that would be sender or reply to. So I think we'll just solve that by types and having a generic type like that. I hope that answers the question. Enjoy the rest of the conference and feel free to grab me if you have any questions. Me and another guy from the Akka team are here. Johan there in the back. Feel free to grab us. Thank you.
Awesome.